Welcome to another video based on Cobb-Douglass production function. Here in this case, we have the Cobb-Douglass production function given as x equals the function in terms of k and l, where k represents the capital um, and l represents the label. So, and then we have a productivity parameter here with this, which is L raised to the power of alpha, and alpha is the capital share, and we also have multiplied by K raised to the power of beta. So we are now asked to compute the following: the marginal product of factors. The factors I have here is both the label and the capital itself. So at first, we will have to find the marginal product of the two factors. So let's pick the marginal product of label itself. So as far I'm dealing with marginal products, the marginal of the product of the factor of label, and that means I'll try to um, differentiate the production function given to me with respect to what? With respect to the to L itself. That is, differentiate the production function given to us, which is x, partially with respect to what? To L. So then how will you go about this? So I need to differentiate um the function given to me over there, which is we have al raised to the power of alpha and k raised to the power of beta with respect to what? Partially with respect to what? To L itself. So then to do this, we believe that we have since the function is in terms of k and L, so we have to consider this whereby a is a constant, alpha is a constant, beta is a constant. But these two factors, they are not a constant, so that means you have to use product through in this case. So when you differentiate this thing partially with respect to L, this simply implies that I'll try to apply the product through formula, which is uv prime plus vu prime. That is, this simply implies take u, we let this represent u, and we let this represent our v, such that we already have our u to be equals to al raised to the power of alpha. Then v prime simply implies we need to differentiate k raised to the power of b partially with respect to L. Differentiate k raised to the power of b partially with respect to L. So I'll come back to for that. Plus, what is v? V itself is k raised to the power of b. And then u prime simply implies differentiate al raised to the power of alpha, okay, partially with respect to what? L. Now what we this is going to give us something reasonable whereby I can decide to write this is al raised to the power of alpha times, can I differentiate k raised to the power of v partially with respect to L? Since there is no L to differentiate in this case partially, all this becomes 0. But suppose there was an L there, I'll just go ahead and differentiate. Since there is no L to differentiate, then everything here becomes 0. So then the next thing for us to do from here is to write plus. Then we have k raised to the power of b. Then can I differentiate a l raised to the power of alpha partially with respect to L? Yes, since this is a constant, this is a constant, and I also have L to differentiate. So it is possible to differentiate this. So that means alpha will multiply the constant, giving us alpha a. Then I have L raised to the power of alpha minus 1. So trivially, 0 times al alpha gives us 0. So we end up having just we have alpha a, we have k raised to the power of beta, then l raised to the power of what? Alpha minus 1. So we can write this as alpha a k raised to the power of beta dot, this is l alpha times l raised to the power of minus 1. So this simply implies that we have alpha a, we have k raised to the power of beta, we have l raised to the power of alpha times this l raised to the power of negative 1 is 1 over l. We all agree with that. So trivially, I believe it is clearly seen that the whole of this expression here represents the production function, which is x itself. So we can let this represent x. So that is alpha x times 1 over L. Hence, we have the marginal product of the factor that is the labor factor, and that is alpha x over L. Please take note of that. So we have just two different formulas. Is it that we use this or we use this? So this is how to compute the marginal product of each factors. So this is for the labor factor. So the next thing for us to compute is we have to find the marginal product of the capital. So now since we have this now, this simply implies the same process. Since I'm trying to look to find the marginal product of the capital, then that means I need to have differentiate. Since I'm dealing with marginal, I'm differentiating the production function given to me partially with respect to what? With respect to the capital itself, which is k. So, and this simply implies that I want to differentiate partially with respect to k of the production function given to us in the question. And the production function given to us is al alpha k beta. That is al alpha, then k raised to the power of what? Beta. And then to compute this, to express this now, we have product rule. We have to apply this rule itself, which is uv prime plus vu prime. And similarly, with what we have actually done here, we have to use this formula, which is uv prime plus vu prime. Now here in this case, this represents my u and this represents my v. So what is u? U itself is a l raised to the power of alpha, then times this v prime means differentiate. V prime is differentiate v, and that is differentiate k raised to the power of b partially with respect to what? Remember, partially with respect to what? K. Okay, so partially with respect to what? With k. So that's what I have for that case. Then plus my v is k raised to the power of v b of beta, and then u prime simply implies differentiate u, that is differentiate al raised to the power of alpha partially with respect to what? K from the question. So in continuation, we end up having al raised to the power of alpha. Can I differentiate k raised to the power of b partially with respect to k? Yes, we can. So this simply implies that I can go ahead and differentiate k raised to the power of b. So that's why I have k in this function. So then this becomes beta times 1, that is beta. Then I have k raised to the power of beta minus 1, so it subtracts 1 from it. So since I have this now, the next thing for us to do is to go to the next term, which is this, that is differentiate al raised to the power of alpha partially with respect to k. There is no k to differentiate here, hence everything here becomes 0. 0 times k beta, I have 0. So whatever I have left now is just al raised to the power of alpha times beta k raised to the power of beta minus 1. So this is what we have, similarly with what I have here. So I can write this as beta a, then I have l raised to the power of alpha k raised to the power of what? Beta minus 1. So this is what we have. Or we can decide to write this as beta a l raised to the power of alpha, this k raised to the power of beta minus 1. Similarly with what we have here, we can split it up as k raised to the power of beta divided by what? Divided by k. So is that if this divides, I have k beta minus 1. So I'll end up having beta. It is clearly seen that al alpha k beta is equals to the production function x, as you can see. So that means we end up having all this expression here as x over k. So therefore we have the marginal product of the capital as beta of x over k. So let's take note of this. The next thing we have to conclude here is that we also have the second question here, which says find the marginal rate of technical substitution. So let's recall with what we have earlier. At first, we believe that the marginal product of labor, we got alpha x over L, right? And at the same time, we have the marginal product of the capital. We have it as beta x over k, right? Beta x over k. And then for us to find the second question we have here, which is compute the marginal rate of technical substitution. The marginal rate, which is MR, of technical substitution is equal to, do you know we have this function in terms of K and L respectively? And that means we end up having the result we have for K, that is M